All right. Hi, everyone. I thought for this week's video, I'd uh, I'd go over the last two quizzes and just kind of give you an example of how I would do these things and how you did these things. And so maybe it might be useful to kind of compare and contrast. Also, I wanted to do a video strictly on series, just so I can set my expectations for grading and make sure that we're all on the same page about that. And what I've seen so far, I've been pretty happy with. But just in case there's any questions about that, so just wanted to run through some examples here. I was asked to kind of cover this stuff, so we want to determine whether or not the given series is convergent or divergent. So the sum n equals 1 to infinity of 1 over 3 to the n. And we're asking, does this converge or diverge? Okay. So we'll recognize this as the form of a geometric series. We'll be a little more explicit and say that this is equal to n equals 1 to infinity of 1/3 to the n. Now it's a geometric series, but remember, to apply this formula, the a over 1 minus r that we know, we have to have the sum in the form a r n minus 1. N goes from 1 to infinity. Okay, so we need to do just a tiny little bit of work here, a little bit of algebra, and factor out 1/3 in the sum end. So that's 1/3 times 1/3 to the n minus 1. And to apply the theorem about geometric series that we know, we verify that 1/3 in magnitude is indeed less than 1. So now we can apply our formula. And this is equals to a, which is 1/3, over 1 minus r, which is also 1/3, which is 1/3 over 2/3, which is 1/2 after we cancel the denominators. Okay, so it's convergent because obviously we found the sum and found the sum of the series, and that sum is a finite real value. So, okay, example. Determine whether or not the series is convergent or divergent. And the given series is n equals 0 to infinity of 1 over 4 plus e to the minus n. Okay, does this converge or diverge? So in the dark, without saying, oh, okay, show that it converges using this test or this test, the first thing we should always do is verify that the limit, if our series is of the form an, right, we need to verify that limit of an is 0 as n tends towards infinity. This is a necessary but not sufficient condition for convergence, meaning that all convergent sums will satisfy this property, but not all sums that satisfy this property are convergent. The most notable example of this being the harmonic series 1 over n from 1 to infinity. Obviously, the limit is n tends towards infinity of 1 over n is 0, but the harmonic series is well known to diverge. So be very careful in how we apply divergence test here. But the first test you should always try is divergence test. If there's any question about which test you're using, it's the easiest one to check, and it can save you a lot of work. So let's see divergence test here. Let's see if this works. So limit is n approaches infinity, 1 over 4 plus e to the minus n. The limit of a ratio is the ratio of the limits. So that's limit as in approaches infinity of 1 over limit as in approaches infinity of 4 plus e to the minus n. And that is a ratio of 1/4 as the e to the minus n goes to 0 as n approaches infinity. So 1/4 is not 0. So therefore, by the divergence test, the series n equals 0 to infinity 1/4 plus e to the minus n diverges. Okay, so generally what I would like you all to do when working with series like this is to say, okay, here's the series, here's the test I'm going to apply, here's why this series satisfies all the conditions that we require for this test. Apply the test, get your result. And if you're on an exam or something, you don't, let's say you're running out of time, it would be a lot better for me to see that you applied a test, applied it correctly, and got an inconclusive result and had to try a second test than to say, okay, well, I'm going to have to erase everything. My first test didn't yield a result. It didn't tell me if it was divergent or convergent. It's much better for me to assign you partial credit to say, okay, well, there was a test that you tried. It might not have been the one that worked, but you did try this test. I can at least give you partial credit for trying to do that correctly. If you erase everything, I have nothing to go on. I have absolutely nothing to go on. So just something to keep in mind there. And again, remember that the limit of the sum n being 0 is not sufficient to conclude that the series converges. Okay. What's next here? Okay. So we want to determine, does the series n equals 1 to infinity n to the minus 2 converge or diverge? So it's pretty easy to see that this is sum n equals 1 to infinity 1 over n squared. We can do that limit in our heads. Obviously, it's 0. So that the divergence test is therefore inconclusive. This series may converge. It may not converge. Or sorry, it may converge. It may not converge. We can't say for certain that it diverges, though. Okay. This one is anytime you see a summand where you think, hey, that might be really easy to integrate, or like this, if this sum were instead an integral sign, this looks like an integral problem. That's kind of a tip off for you that you may want to use integral test. I'm not saying that it is necessarily the easiest thing to do. Sometimes there are other tests that work. We're at a point where math, or there's a lot more art than science to this. Outside of a very few specific examples, it's difficult for me to tell you, okay, all series of the form test like this, all series of this form test like this. This is something that just kind of comes with experience and doing a lot of them. Additionally, this comes with an increased level of rigor that we'll be expecting. So this is why students tend to struggle with this so much, is because we're asking more of you to show that these things converge or diverge more rigorously than you probably have done in the past. And there's no hard and fast rules for a lot of these. So it's kind of a double whammy of complication. But so what I'd like to see is we say, okay, we're going to apply integral test. Okay, now we need to justify why we can use this test. Okay, so suppose we have a function f of x is 1 over x squared. Okay, so for integral test, we need to satisfy a few conditions. Okay, so we need our f to be continuous. We need it to be positive. We need it to be decreasing. And we want it to be on the interval 1 to infinity because that's what's going to match our bounds. Okay. Most often you see this theorem stated in terms of 1 to infinity, but there are times when we might want to do, say, 3 to infinity or 2 to infinity, that kind of thing. But we just need it to be, for this one to match 1 to infinity, we want it to match here on this interval 1 to infinity as well. Okay, so the theorem says that if the improper integral of f from 1 to infinity converges, then the series converges. If it diverges, then the series diverges. So they either converge together or they diverge together. So first we need to justify why f satisfies these properties, okay? And on 1 to infinity, on the interval 1 to infinity, f of x is differentiable, which implies that f of x is continuous. You'll remember that, again from Calc 1, continuity is a necessary but not sufficient condition for differentiability. So differentiability implies continuity. Okay, so f is continuous, check. Is f positive? Well, f of x is 1 over x squared. For x non-zero, in fact, f of x is positive because the denominator is getting squared. But really, we're just interested in x belonging to 1 to infinity, so that we also have f of x is positive there. So check mark. And then decreasing. Decreasing is a little difficult to show algebraically, but we have this wonderful tool called the derivative. So if we show that the first derivative of f is always negative on the interval 1 to infinity, well, then we're in luck. We're decreasing because we always have a negative derivative, right? So we can calculate that f prime of x is minus 2 x to the minus 3, which is minus 2 over x cubed, right? So for x being positive, the cube of x will also be positive. So for x in 1 to infinity, f prime of x is negative. Okay, so that tells us that it's decreasing. All right, so now we have an f that's going to work for us. Okay, we had to justify why it's going to work, but now we have it. Let me just erase a little bit here. Okay, so now we consider the integral from 1 to infinity of f of x dx, 1 to infinity of 1 over x squared dx. And now this is how I'd like to see improper integrals happen. We pass to the limit 0 to t as t approaches infinity of 1 over x squared dx. And that's the limit as t approaches infinity of, if we integrate this, we get minus 1 over x evaluated from 1 to t. Which is the limit as t goes to infinity minus 1 over t plus 1 over 1. And as t tends towards infinity, this term goes to 0. This has no t's in it, so it's unaffected by the limit. So our limit is 1. So we conclude, therefore, the integral from 1 to infinity, 1 over x squared dx, converges, which implies that the sum, the series, 1 over n squared, converges by integral test. Okay, so like I said, much more rigorous than previously we have done. As a little fun fact, this is extremely counterintuitive, but the sum from n equals 1 to infinity of 1 over n squared is actually pi squared divided by 6. So it's not generally very difficult. It is generally very difficult to evaluate the what a series equals. In some cases, like geometric series, we can find formulas for it. In general, that was very difficult, and this one is, like I said, a very counterintuitive thing. Don't ask me how it makes sense that adding up a bunch of integers gives you irrational numbers in a numerator, a bunch of rational numbers, I should say. Adding a bunch of rational numbers yields an irrational number in the numerator, but it does. I think it's kind of beautiful. So, all right, let's do another example. Determine whether or not the series converges or diverges. So we have the sum n equals 2 to infinity, 1 over n log of n squared. So first we want to check if we take the limit of this. Well, we just have two limit as n approaches infinity. That limit will go to 0. So the divergence test doesn't help us out, but it tells us that this integral may possibly converge. Okay, so this to me looks suspiciously like an integral, right? If this were x instead of n, well, this looks pretty much like a straightforward u sub. So I'm going to say apply integral test. So let f of x equal 1 over x log of x squared. Okay. So again, we need to justify on 2 to infinity, f of x is differentiable, right? Because the denominator is defined on 2 to infinity. And it's just a product and ratio of differentiable functions. And since we don't have any domain issues, that itself will be differentiable. So that implies that f is continuous on that interval. And then for values of x larger than 1, log of x is positive. And obviously x is positive. So we have f of x is greater than 0 on the interval 2 to infinity. And then the last thing we need is decreasing. So we check the derivative. So I'm going to rewrite f of x as x to the minus 1 log of x to the minus 2, because that's a more calculus-friendly form. We apply product rule. So f prime of x is, I'll differentiate this and then leave this alone. So that's minus x to the minus 2 log of x to the minus 2 plus, and now I'll differentiate the second term and leave the first term alone, or sorry, the first factor. And that's minus 2 ln of x to the minus 3 times 1 over x by chain rule. So that's minus 1 over x squared log of x squared plus 1 over, minus 2 over x squared log of x cubed. And again, the denominators of both of these are going to be positive on the interval 2 to 1. So we have a negative thing minus a negative thing, or sorry, a negative thing, and then we take away more from it. So we conclude that this is less than 0 on the interval 2 to infinity, which implies that f is decreasing. So now we're in a position to apply integral test. We've shown that our f is a function that satisfies the necessary conditions to apply the integral test. Okay. So now we consider, and here's where I'm saying we'll switch the bounds to 2 to infinity. 1 over x ln of x squared dx is limit as t approaches infinity 2 to t 1 over x ln of x squared dx. And off to the side here, I'm just going to find our antiderivative. So just looking at 1 over x ln of x squared dx, let u equal to ln, u equal to ln of x. So du is 1 over x dx. So this just becomes 1 over u squared du. And when we integrate that, what do we get? That's minus 1 over u plus c. But since this is side work, we're not really going to deal with the c. So this is minus 1 over equals minus 1 over ln of x, back substituting, plus c. Okay. So just to make room, I'll go ahead and erase this and put this little box here. Ln of x plus c. Okay. So this is equal limit as t approaches infinity, integral 2 to t. Well, I suppose since we have the antiderivative, we can just go ahead and skip that. So this is minus 1 over ln of x evaluated 2 to t, which is limit t approaches infinity, minus 1 over log of t, and then the minus signs will cancel out, plus 1 over log of 2, right? So now we're ready to take the limit, and we'll see that this indeed goes to 0 as t approaches infinity. And this is just a constant with respect to the limit. So our integral from 2 to infinity of 1 over x ln of x quantity squared dx sorry, I had to sneeze. 1 over x ln of x squared dx is equal to 1 over log of 2, which is obviously convergent. So we conclude, therefore, the series n equals 2 to infinity of 1 over n log of n squared converges by integral test. Okay. And then again, just wanted to really hammer this home. If we take a look at something like 1 over 2 plus 10 to the minus n, right? Always look to use your divergence test because it is a very powerful thing and it saves you a lot of work just it can save you a lot of work. It's just something that you should always check, and then it rules out the easiest cases, right? So if we look at, so consider limit as n approaches infinity, 1 over 2 plus 10 to the minus n, well, that's just what, 1 over 2, right? Which is non-zero, and that implies that the series n equals 1 to infinity, 1 over 2 plus 10 to the minus n diverges by divergence test. Always keep an eye out for that. It's going to make your life a lot easier. Okay, I think that's about all I wanted to cover in this particular one. So if you have any questions, feel free to let me know. I'll try and get to them as quickly as I can. Thank you.